As the title says, I'm talking mostly about permeation. So let's first spend 1 second saying what permeation testing is. We have some hydrogen creation environment on one side. We have our specimen, which we are studying in the middle, and then we have diffusion going through. And then on the other side, we have some kind of measuring device. We measure the kinetics at which hydrogen leaves the specimen, but for example, changing the hydrogen entry input concentration that we put there. On the figure, I have represented the standard amount and essentially double shell, so it has a electrochemical by both sides, but these things I will say are not dependent on this. From this, we obtain a curve which measures the hydrogen outgoing flux against time. From this, again, why are we doing this? Because we want to obtain information on the material's diffusion and trapping behavior. We want to obtain a model which is able to predict how hydrogen diffuses in different conditions than when we test it, obviously. Why is this useful? Well, there are many reasons. The origin of this comes from the automotive sector, where they would like to do risk assessment from internal hydrogen. So they'd like to know how much it accumulates, how much it outgasses, and so on. But we've recently moved, as 2 presentations ago has shown with Baker-Hughes, but we also had a collaboration with Eni. So we have moved into the energy sector, where due to NDA, I cannot go into details, but both companies are interested on this, on modeling the hydrogen diffusion and trapping. So it's useful. Maybe why could it be useful? Well, very basic is we would like to design testing procedures. I'll give you one example. We'd like maybe to charge hydrogen, gaseous hydrogen at room temperature. How can we do permeation at room temperature? Very difficult. Maybe very little hydrogen is there. But if you want to do some testing, you want to do saturation, we would need to predict how much time it requires to reach saturation. If we have a model that is maybe able to extrapolate the diffusion at different hydrogen concentrations, we can get an estimation of this, at least, without doing permeation tests with gaseous charging at room temperature, which is very difficult. But another reason could be, for example, to interpret mechanical testing results. I distinctly remember one paper, which I can't find anymore, where they compared experimental hydrogen depth inside of in situ charged specimen and predicted hydrogen penetration depth. From the difference between these two, they made some conclusions. They observed one by watching the fractography. They made some conclusions. This is a way in which information on diffusion helps us interpret mechanical testing. But also, what we are trying to do in a different context is trying to do mapping, for example, by simulation inside of our ex situ test specimens. So there are many reasons why someone may be interested in this. Very, very quickly, I will bore you with the continuum models of hydrogen diffusion and trapping that we are using. McNam and Foster, one of the most, the oldest ones. It is able to include mass conservation. Diffusion is only due to lattice diffusion. Trapped hydrogen is immobile, which is the only strong assumption of this. I would call it strong assumption. We have many papers talking about grain boundary diffusion and so on. This can be used here, it can be modeled here, because trapped hydrogen is immobile. And then the trapped hydrogen kinetics, which depend on very many parameters. But this is usually not used directly. Usually, Oriani's model is used, which we can obtain if we move from this and assume local equilibrium, which it can be done mathematically a few different ways, but I don't want to go into details now. The point of Oriani model is, well, we have at this point, we lost the kinetic, and we can put it all together in the first equation. And from this, the hydrogen effective diffusion coefficient comes out. This is something which depends on concentration, it depends on time, it depends on position. So it's something that is not terribly easy to model. We have to use models like was shown 2 presentations ago. Another step can be to now assume low trap occupancy. Low trap occupancy. In which case we go back again into something which is functional equivalent to fixed model, asterisk there, by having a Bay effective which is not dependent anymore on hydrogen concentration. This comes again immobile traps, fast traps, and low trap occupancy. Why did I say all of this? Because all of those models now come into play when I will talk about the meat of my presentation, which is from a permeation transient, we would like to obtain the trapping parameters. This is commonly done following this procedure. We obtain from this the very basic parameters, so initial final hydrogen concentration from the flux, and then the D-lag, for example, which is a measure of the apparent hydrogen diffusivity. This is a, let's call it, technological property. It depends on this test. This is the apparent diffusivity of this test. If I change hydrogen concentration, I change apparent hydrogen diffusivity. If I change thickness, I may change apparent hydrogen concentration. If I change temperature, clearly, I change it. And then from all of those, using different formulae present in the literature, we try to estimate trapping parameters. Those are the most common I found. The first one is called Oriani-Don, even though it's basically Oriani. The second one assumes deep trapping. And the third one is found in the original McLaren-Foster paper. What I will do today is show you a generalization of the third one that we found, and that we have a paper under minor revision. So let's hope it comes out recently. It will come out in the near future. So to do this, I first have to discuss the problems of the third one. Here is a paper of Diaz et al., which I cannot stop thanking because they gave us the spark to do this research here. McLaren-Foster, to obtain this formula, just assumed initial hydrogen-free conditions, final linear steady state of a permeation test, so we have 0 hydrogen on one side and some amount of hydrogen on the other, Dirichlet boundary conditions, very important, and then they obtain this formula. This is analytically derived using those conditions there. So we can just do the same process that they did using a different initial hydrogen concentration. This is the problem Diaz observed of the original formula. They said you should not use this because it assumes initial hydrogen concentration. Okay, we can analytically derive. It's a little bit more complex because it has more parameters. But this is, again, analytically derived from McLaren-Foster. There is no extra assumption instead of, apart from those written there. And this can now be used from a permeation transient to obtain trapping parameters. And I will briefly show how this fares comparing it with the other papers, with the other formulae present in the literature. So, first of all, let's observe that it is really a generalization of also the other ones. If I take this generalized McLaren-Foster or the classical McLaren-Foster, and I assume low trap occupancy by doing this Taylor series here, I obtain Oriani-Don expression. So this is fine. If I assume deep traps, and I have to use the old one because with initial trap, if you have non-hydrogen-free initial conditions, deep traps are saturated, they don't do anything anymore, I obtain TNF1 formula. So both McLaren-Foster's formulae are generalizations of those. That means clearly those have baked in those assumptions there. And I will show it when we discuss now that by using one of those formulae, whichever we want to use, which basically are prediction formulae, they take in material parameters and test parameters and they predict D-lag using the effective method, using the derivation of McLaren-Foster, or using our new ones. We can just use them as they are used in the literature to solve the inverse problem. So we measure D-lag experimentally for some tests, and then we try to find the the material parameters which reconstruct or would predict the same experimentally measured D-lag. Very briefly, the procedure is this. We take experimental data, we use all of those formulae to try to predict material parameters. And how can we see how those material parameters really fare? Just put them back into Oriani's model, simulate the original tests that we had, and then compare how much the curves are actually reproduced by using those parameters. Now, all of this can be solved if someone uses, like shown in the previous conversation, in the previous presentation from my colleague, directly the model, and we fit. But that's a little bit more intensive. We have to have the model, and solve it repeatedly to make fitting. Here I have direct expressions which can be fitted much easier. They're robuster and analytically less complex. So that's what the advantage is of this. I have taken here some data from the literature. I've forgotten to change here. Current density is proportional to hydrogen flux. I'll say this just because I have not went into detail on the Manhattan-Stachursky double cell. I've taken this experiment from the literature where they did repeated stepwise transient, which is something which is important to make use of the new expression. This is useful because at lower hydrogen concentrations we have lower diffusivities, so we can actually measure the transaturation effect. And I've taken all three formulae. The one with deep traps I've not used because it would just give horrible results because we are not in the deep trapping regime, and used the best fit parameters by using the expressions to reproduce the curves. And what we can see, the new expression has a better reproduction of the curve. But why is this? This is the most interesting thing, according to me. Here in the graph, I quickly show, okay, here I had just transient index. Transient 1, 2, 3. Black points are the experimental apparent diffusivity. And by using the best fit parameters, I here show what the three formula would predict. Orianidon assumes low trap occupancy. It has no way to distinguish this and this transient. So it just predicts the average. That's the problem. Whereas the old McCabe-Foster, that was used by Diaz, and they said you should not use it, correctly reproduces the apparent value. But what about the curve? As I said before, this assumes initial hydrogen-free concentration. So actually, in the real simulation, most of the hydrogen traps are filled. We are in saturable trap regime. So this formula overestimates the trap slowing effect. So if I use the parameters that come from this formula and simulate, I get that my simulation is faster because the formula does overestimate this value here. Whereas the new formula does correctly capture the saturation effect, not only on this graph, because it has inputs for the hydrogen concentration, but also on the final graph of the simulation, because it correctly captures the effect of hydrogen concentration on the T-lag by having non-zero hydrogen concentration. Yeah. So I will just close by very briefly summarizing. We have a formula of T-lag prediction, a new one, which is able to correctly see the trap saturation effect. It can be used in an inverse way to do parameter estimation, like all the others were used. We have a case study where I showed that it is better, and discussed briefly why it's better. It's robust and expensive algorithm because it's a formula. We don't need to do a model solution for permeation. And then I have a few extra observations that may be interesting if someone has studied permeation a little bit. The formula is symmetric by swapping initial and final hydrogen concentration, which is not intuitive, but it's interesting to explain why. The formula is easily extendable to multiple trap types. And if my revision goes through, I hope you'll see this in the new paper. And there is no effect of trap kinetics, even though we've derived directly from McCabe-Foster. This is also something which is not automatic, but it's interesting to discuss why it is. Then I'll just close by saying this will be used, for example, to compare non-prestrained and prestrained materials. We wanted to show those results, but we had an issue with some tests we have to repeat, so they're not ready for today, but this is something that we're trying to do, so see the difference in the trapping parameters by changing the material. Thank you very much for your attention.